have the program almost finalized for the conference that will take place in a few weeks. And one anecdote that I wanted to mention, I was attending a conference in Palo Alto last week, and this was a conference about the search for life throughout the universe, and one of the talks was entitled, "Why Aren't Clouds Green?" When you come to think of it, you look at the sky, the clouds are white, but they have a lot of microbes actually. The seeds of the nucleation of droplets, water in the atmosphere, are microbes. And so an interesting question is, why don't you have an ecosystem within the clouds that make them green? That's not trivial. So there was a whole talk about that, and the fact that the UV illumination from the sun kills some of them, and they don't have a finite lifetime. They do have a finite lifetime, and so in this vein, actually, it reminded me of the situation with black holes, because originally when quasars were discovered, there were some people suggesting that they're actually white holes, and the suggestion was that there are possibly naked singularities that are emitting a lot of energy. And then it was realized that they are most likely black holes, and obviously the observations of the Event Horizon Telescope will be able to tell us conclusively whether there are black holes or not. So it's just interesting that the color of things matters a lot in terms of the physical content. And today we have one speaker, and Raz will introduce him. Perfect.
Well, it's a pleasure to welcome Martin LeSourd to the Black Hole Initiative Colloquium Series. Martin is a DPhil student at the University of Oxford in philosophy. He completed an undergraduate degree from the University of Cambridge. Prior to that, we had the benefit yesterday of hearing him tell us about a new theorem on singularities that he has. So this is based on a paper that you can read about on the archive. That was a lot of discussion, and today he's going to tell us about something different from that work, namely various aspects of evaporating black hole space-time. So, Martin.
Thanks for us. So, first of all, I should thank the organizers here, the people that are making all this happen, and thank Eric as well for inviting me here, giving me the opportunity to learn and to work with people and to present some of my work. So I'm extremely grateful for that, and I'm very happy to be here. And this is going to be it's going to be hopefully a relaxed talk. So if you'd like to interject at any point, if there's something that's not clear, or a certain definition you'd like more information on, or something like that, then I'm more than happy just to stop in en route. So I'm going to start. It's going to be a whiteboard talk. I normally use the blackboard. I prefer that, but the whiteboard here is a lot bigger, and I've got lots of things to say. So the title is going to be Causal Properties of Evaporating Black Hole Spacetimes. So we're all interested in these types of spacetimes. None of us know how it works. And the point of this work was to try and use precise mathematical language to start talking about them. So you can use the kind of underlying geometrical framework for classical general relativity, Lorentzian geometry, to try to think about how you'd capture the structure of such a spacetime. And the point behind this work was to do so based on earlier work that had been done, and to use some of the earlier notions and earlier theorems that had been proved, and to ask the question whether it's possible to add certain premises to those theorems and to derive further consequences. So in particular, I'm going to be talking about three things, but essentially the punchline is going to be, yes, you can take these old theorems, add new things to them, and get more information out. So that'll be part two. In part one, I'm going to talk about the causal ladder. I'm going to just introduce some basic notions of the causal ladder. So just explain what that means, what that is, some of the physics behind it, some of the physical intuition behind it. Then I'm going to talk about the old and new results, right? Which are mathematical results, so they're theorems. They're just theorems of Lorentzian geometry. And 3, I'm going to talk about physical implications, if any, of course, because I'm dealing with a classical space-time structure, so one may ask, well, you're dealing with a quantum gravitating idea or object or postulated entity, why should I trust my classical physical description of the system? So that's a definite point of debate, and I'll talk a little bit about this, and some of the philosophical implications of these results. So there'll be 3 parts. I'm going to split these. I'm going to split the talk roughly equally in these 3 parts. So first of all, to define the causal ladder, I'm just going to give you a little idea of what the whole background structure is. So I'm dealing with a Lorentzian spacetime, with the Lorentzian metric, all the standard properties, all the standard topological properties, which I'm not going to list, but you'll find them in any textbook. And in particular, G will be C3. So notice I've got differentiability, which is not smooth. In the usual case, I don't need that here. And the dimensions will be greater or equal to 4. The theorems that I'll be describing will work for a scry, which is defined by a kind of slightly more precise notion than the classic ones, where M embeds into M tilde with a suitable conformal factor, which, by the way, will also be C3. So this is just my background structure. I'm just putting that to one side for now. So the causal ladder. What is the causal ladder? So if you study Lorentzian geometry and you love playing with the idea of causality, then the causal ladder is probably the most important object you look at and you study. So what the causal ladder is a list of definitions, each of which are stronger or weaker than the next, that capture some causal property of the spacetime. So there's a theorem for each of these levels, which imply the next theorem, and there are counterexamples to show the direction doesn't go the other way around. So mathematicians are not renowned for their humor, but in fact you'll see as some of the definitions will be said, you'll find maybe some of them quite funny. At least I do. Non-total imprisonment is the first one that's kind of funny. Then there's just causality, which is kind of standard. Chronology, absence of closed time-like curves. And my favorite, non-totally vicious.
And you would define this, of course. Yes.
So, what are all these definitions? All these definitions capture some property of the spacetime. So if you're globally hyperbolic, of course, it's a very well-known theorem, very beautiful, that in fact your spacetime arises as the development of a Cauchy surface. In other words, you could say the spacetime is predictable, and you can show that GR as a vacuum PDE system is well posed in the sense that you can go through the machinery of what that means. So continuous dependence of initial data and all the rest of it. Very important thing. If you study, by the way, if you study PDEs, which in the mathematical community these days, that's what a lot of what people do, at least in the hyperbolic world. The elliptic world, they just look at data sets. But in the hyperbolic world, they do PDEs. So if you talk to someone who's working in PDEs and GR and you tell them, oh, I'm looking at a stably causal but not causally continuous spacetimes, you say, wait a minute, what? I'm doing global hyperbolicity. I've just got PDEs. I've got well-posedness. So yeah, there's a whole lot of GR, which is not of this PDE kind, but there's a whole bunch of people working just in the PDE kind. So it's just a little side comment. So this is, the next one is when it's causal and J plus minus is closed, where that's defined as the future of any point. So any Q such that you can draw a future-directed timeline curve from P. And you'll notice, for example, that Minkowski spacetime, if I remove a point and I consider the future light cone, then I'm no longer closed. So Minkowski spacetime, with a point removed, I'm banning those spacetimes if I'm causally simple. I'm going to come back to causal continuity because that'll be the main thrust of the talk. So for stable causality, the definitions
Are these supposed to be subsets of one another, or what do the arrows mean? We've got arrows between all these definitions.
Yeah, so this is, yeah, I should just say equal.
No, he meant the arrows down.
Are they all subcases of the one up on top of each other?
So if you're globally hyperbolic, you're causally simple. If you're causally simple, you're causally continuous, and so forth. But if you're causal, you're not necessarily non-totally imprisoning, and vice versa. So
the arrows are logical implication.
They're logical implications, right? And this is to show that if I take Minkowski spacetime and I remove a point, then I'm no longer causally simple. Why is that? Because J plus is not closed anymore. Why is that? Because I can get an L geodesic hitting this point, and then this guy is on the boundary of J plus and it's no longer in J plus because I can't draw a curve from here to here, and therefore J plus is not closed.
But what's example of a causally simple spacetime that's not globally hyperbolic?
So I could take, for example, a strip in Minkowski spacetime, and I could consider, so recall that globally hyperbolic is the compactness of the intersection for any 2 points, and that the spacetime is causal, so that was an improvement from the previous theorems. But basically I can consider a strip in Minkowski spacetime, remove the points, and then I'm clearly when I consider the intersection of these guys, I'm clearly not compact anymore. So a vertical strip in Minkowski spacetime is not globally hyperbolic, but it's causally simple. Okay. So I'm going to talk about causal continuity later on because it's going to be very important. For stable causality, I'll just say that there's no almost closed causal curves.
But isn't that implied by global hyperbolicity?
Sorry, what was that?
Isn't that implied by global? Isn't that already true at the top?
So remember, this is logical implication. So if the spacetime is globally hyperbolic, it has to be stably causal. But a spacetime can be stably causal and not necessarily globally hyperbolic.
But
So
don't the globally hyperbolic ones have no closed timeline curves?
Of course.
So why are you only mentioning when you get down to the fourth category?
He's just giving definitions.
Because I'm just giving definitions of what each of these levels mean. So if I'm this, I'm that. But if I'm this, I'm not necessarily this, or that.
I see.
So for closed causal curves, basically you can think of a light cone. There's a rigorous mathematical definition. It'll take me a little bit too long to fully define it, but basically you should think of this as if I open the light cones a little bit, if I consider a metric G, which is kind of inside G0, where this is some reference metric, then when I open the light cones a little bit, I don't produce a closed causal curve. So it's also an important theorem that if you're stably causal, then you can foliate the space-time with the level sets of some global time function. Some global time function is a function that increases on any future directed causal curve. So stably causal space-times admit a notion of global time. A strongly causal space-time is one where, again, the fully mathematical definition is that there are no arbitrarily small neighborhoods such that when I leave this neighborhood, I don't intersect it again. But you can just kind of see it if I take Minkowski spacetime and I identify these two lines, and then I consider removing some lines from the spacetime. These are going to go on forever. Then notice that there is a curve here, such that if I'm moving here, then I come back here, and then I can consider zoom in on this point, and then I've got a neighborhood where I've got a curve that comes in here, and it goes back. And so I've intersected the same neighborhood. I can make this neighborhood arbitrarily closed, arbitrarily small. So I'm not strongly causal. So I'm banning, again, these types of examples. Distinguishing space-time is when, this will be important for us later on as well, is when if the past or future of any 2 points is the same, that implies that P equals Q. So in other words, if I have the same past, then I'm at the same point. Non-total imprisonment is going to be less important for us, but you can just kind of think of it as being some inextendable causal curve that gets trapped in a compact set C. So this would be a totally imprisoning spacetime, so non-totally imprisoned spacetime is one that doesn't do this. This just means no closed causal curves, and this means no closed time-like curves. And non-totally vicious is that the future or past of any point P is not equal to the full space-time for all P. So that's very weak. That's just take Minkowski space-time and delete everything north and south. Take as identify two horizontal lines so that my topology is now S1 cross R, where S1 is the time direction. Notice then that I can go back and forth forever, and that the future of any point P is in fact the whole space-time. So I'm banning this when I'm saying that the space-time is not totally vicious. Okay, that's probably enough for the causal ladder. I mean, we could spend 10 lectures on this beautiful thing, but I now wanted to talk about causal continuity because that's going to take a specific role in our case. So what's causal continuity? I'm going to define a little bit more precisely because actually I'll be arguing later on that when you take natural seeming hypothesis from the classical perspective of what an evaporating black hole space-time, then they'll be not causally continuous. That'll be the punchline of the talk, but for now I'm just going to define causally continuous so that we have a better idea of what it is. So causally continuous space-time is distinguishing, and it's reflective. Or, I can define it another way, the future and past are outer continuous. Now I'm going to define what these mean. So if the space-time is reflective, what that means is that for any point P, if there's a point Q which lies in the future of P, then that implies that in fact the past of P is inside the past of Q. So in other words, I can reflect this down and I've got this going on. So reflectivity is that whenever I'm in the future of something, then I'm in the past of the other guy. And outer continuous for these functions I plus means that for any point P, then the future of this point, I of P, is such that if I consider any compact set, K, that lies outside the closure of I of P, so K is inside the closure, outside the manifold minus the closure of I of P, then it follows that I can find a neighborhood around P, U of P, such that any Q in U of P has the property that the future of such a point does not intersect, such that K does not intersect the future of such a point. So choose Q such that K is inside M, not in I of Q, the closure of I of Q. So basically what that means is that if I've got any point, I consider its future. If it's outer continuous, then I can consider something outside its future, and I can always find a neighborhood sufficiently small such that any point in that neighborhood, its future will also not include this K. Okay, good. I think that's enough for the causal ladder. Now I'm going to go and talk about these old and new results. So where they come from. So the first idea came from Hawking's argument from 74, 75, where argued that black holes could evaporate. And then in 79, Kodama, and then later, Wald and Geroch put forward a kind of rewiring of this theorem by Kodama. So what Kodama was trying to do was to take kind of natural seeming definitions for what an evaporating black hole spacetime is, and he wanted to prove something about these. So Hawking had argued that they evaporate. He had argued that they're probably not globally hyperbolic. Then there was the information paradox. That was the start of it and everything. But he didn't actually prove that under certain conditions that you would think naturally characterize what an evaporating black hole spacetime is, at least from the classical perspective, that they have such and such properties. So Kodama, under a certain construal of what these properties might be, actually proved that these spacetimes have to be non-globally hyperbolic. Of course, his assumptions are intuitive. There's no way you could really check them if you didn't have it, if you didn't really know what was going on. So they're just a proposal. They're just a suggestion. But then Wold wrote an article in '84. By the way, he still holds the same view that he had in that article '84. He told me this, so I can tell you that he still stands by those arguments. Wrote a paper in '84 based on a rewiring of this result by Kodama, which Bob Geroch apparently suggested to him. So what is the theorem? So I'm going to describe it to you, then I'll draw a picture, and the picture will hopefully represent roughly what's going on. So the theorem says let S1, S2 be two partial Cauchy surfaces. So these are candidates for the locus of initial data. Now, we're going to prove they're not globally hyperbolic, so these are not actual Cauchy surfaces, but they're slices in space-time that, if it was globally hyperbolic, would be candidates for the Cauchy surface of the space-time. And then, so this is assumption 1. Assumption 2 is that there exists a P which is not in the future or in the past of 2, and then 3, JK intersection S2 has compact closure when K is defined as follows: S1 minus the past domain of dependence of S2 intersection with S1. Where the past of domain of dependence, just as a reminder of what that notion means, it means that from some set S, the past of domain of dependence is any point here such that when I draw any future directed causal curve from any such point, I have to intersect S. So for such a set, the past domain of dependence will look something like this. So, under assumptions 1, 2, and 3, you can show that any space-time which harbors such things has to be non-globally hyperbolic. So why is that nice? Well, we can think of this picture in terms of the standard Penrose diagram that people like to draw. Well, maybe I should draw a bigger diagram. So, I mean, there's a few diagrams I want to draw, but here's one I could draw. So the idea behind these kinds of conditions was that if this is an evaporating black hole, so it forms and then it kind of disappears. This will be my evaporating black hole. This was the picture. If this is S1, if this is S2, then there exists a P inside there which I cannot reach from S2. And the past domain of dependence for this guy is going to be the shadow of this evaporating black hole. So the past domain of dependence will be all of this set outside here. And then notice that if I take the intersection of that with S1, then essentially I'm along this slice, everything outside this shadow. And then when I take the complement of that in S1, then essentially I'm dealing with this set K here. So I'm looking at the causal shadow, if you will, caused by the evaporation of a black hole. K, and then what I do is that I consider any possible future causal curve from the set K, and I consider its intersection with the later time slice S2, and I require that this has compact closure. You can think of that as saying that there's some kind of finite extent of the size of this set. So if we think of the standard Penrose diagram, of course this is much more general than the standard Penrose diagram, but if we think of that diagram, then we have something like this, and then S1 is here, S2 is here. The past domain of dependence of S2 is going to be this set here. Then K is going to be the complement of this guy, so it's going to be this set here. And then the future of K is going to be everything up to here. And then this set here is going to be J cross K intersection S2. So certainly a standard Penrose diagram is captured in these assumptions. And in this picture, which is kind of more general, which I prefer, you can also see how these conditions may be natural from one perspective. And then essentially, you can show by a relatively short argument in causality theory that such a space-time must be non-globally hyperbolic. So to my knowledge, that's kind of the best argument that we have for saying that these space-times are non-globally hyperbolic. It's an actually rigorous argument, which is based on these more or less natural-seeming assumptions. Of course, we have no way of knowing if this is really what happens. We don't have a theory of quantum gravity which is, which would show us that these are exactly what happens. But it seems natural from one perspective, at least, that you might buy the premises of this argument. Of course, I'm willing to be told otherwise by those who are versed in issues of quantum gravity, which I certainly am not. So this is the old result. Now I'll be presenting the new result, which is work that I've done, which will be upcoming. So what does it say? Well, the first thing I'm going to do is I'm going to embed this whole thing. So I'm going to require that I've got M embeds into M tilde by means of a suitable conformal factor, and my scry can be either space-like, null, or time-like. So in particular, I'm hoping to cover cases where the boundary can be empty de Sitter, or flat. And then I'm going to require something else. This is the key condition, and I'm requiring it, and we may debate about it, whether it's right or wrong, but I'm assuming that for any complete null geodesic entirely contained in the past of future scry, intersection with the future of past scry, so this is otherwise known as the DOC, the domain of outer communication. Then, for any complete, then intersects the boundary scry in M prime, M tilde. What that means is that if I'm a black hole, I'm here, and I've got some scry boundary, scry plus, scry minus, then what the condition is saying is that for any complete null geodesic that's outside, well, in fact, I'm going to reach the boundary. Now you may ask, well, that's actually a rather reasonable condition. I mean, it would fail, for example, if I had some null geodesic that would get totally imprisoned in some compact set outside the black hole region, the evaporating black hole region, and that would imply a fairly pathological structure anyway from our considerations early on in the causal ladder. You may say, well, what if I remove points elsewhere? Then I'm not going to be complete, so actually that's not a problem here. Or you may do things like conformally rescale the metric within compact regions so that the conformal factor stops your geodesic from reaching scry without these geodesics being incomplete. Again, that would be fairly pathological, so I'm ruling this out. Now you might ask, well, do typical black holes actually satisfy this? The answer is no. Why? Because if I have a black hole, which I can consider, say, by some cigar, some tube forming, then I'm a null geodesic here, and then it's known that there are orbiting null geodesics go around the black hole. But the idea behind this condition is then to say, well, actually, once the event horizon has kind of ceased to exist, I don't know how, of course, this process happens, but once these would-be orbiting null geodesics, what happens is that they kind of escape, because they're no longer trapped. So although a typical black hole traps null geodesics within some finite radius of the event horizon, I'm assuming that when the black hole is no longer, then actually these would-be trapped null geodesics can make it out to scry. That's the key point of my assumption. But then the result is that you can then show that it's a theorem. It's a theorem that if 1, 2, sorry.
Martin, so you're also assuming the 1, 2, and 3 of Geroch-Wald?
Sure. I'm going to write that down in the theorem. So it's a theorem then that 1, or I, double I, 3I, plus 1 and 2, plus 1 and 2. It's a theorem that if you have these 5 conditions, well then in fact, Mg contains naked singularities null on the Cauchy horizon of S1, and furthermore, the spacetime is causally discontinuous. So what does that say? That says that if you're considering what an evaporating black hole spacetime might be within the realm of possibilities offered to you by Lorentzian geometry within this classical mathematical framework, then you can show that these kinds of pictures, these kinds of arguments, lead to a fairly pathological spacetime. Not only is it not globally hyperbolic, it's in fact worse. It's causally discontinuous. Now, there's a way of seeing that, or there's a way of illustrating that, again, with the standard Penrose diagram, which is really serving an illustrative purpose here. There's nothing that I'm not basing any real argument from this. But you can kind of see that as a means of illustrating this, that if I pick a point here, and I consider a point here that's, say, causally related, then I could consider their pasts. Now their past is going to be such a set. And then here's another past. Now notice that for P1 and P2, I of P1 is inside I of P2, I minus. And so this is coming back to the reflectivity property, which we had listed down before, which I've now rubbed away. But notice that this does not imply that the future of IP2 is contained in the future of IP1. So it's not reflective. Furthermore, you could consider this diagram yet another time and consider some point here, and you could consider the future of this point, and you could consider some compact set here, say K again. Now K is obviously not in the future of this point, P1, but K is in fact, if I consider a neighborhood of P1 and I zoom out, this is the event horizon that's going through it, and furthermore I assume that, well, I don't assume anything here, I'm just saying that it's for any K outside here suitably chosen, then I'll have a point Q in arbitrarily small neighborhoods such that in fact the future of Q, say it's here, is in fact going to contain the compact set. So my ability to find such a neighborhood is broken, and the spacetime is therefore not causally continuous. So far, I've kind of gone through a little bit about what the causal ladder is. I've kind of reminded us of the arguments by Kodama and the reformulation by Geroch and Wald, which is kind of like an argument for the non-global hyperbolicity of such spacetimes from seemingly clear assumptions. And
So your theorem goes 2 steps
Yeah,
higher
exactly.
in the ladder.
Yeah.
than
So
the-
exactly. So you could see the theorem as saying. So you could see the initial theorem as saying, evaporating black hole spacetimes for one perspective are not globally hyperbolic. That's what Kodama and Geroch and Wald are saying, and it's the most precise, rigorous argument to that effect, at least that I know of. I'm very happy to talk about other ones if people know of others, but insofar as mathematical rigor and stuff is concerned, this is the best argument I know of. And then what I'm saying is that actually if you add these 2 conditions, which are rather natural perhaps from one perspective, I mean I'm just putting a scry in the thing and then I'm assuming that these null geodesics can escape, well then in fact you can push the causal structure, as you were saying, you can push the causal structure down not only to causal continuity but to stable causality. So in other words, from the classical perspective, from the general relativistic classical perspective, evaporating black hole spacetimes, at least under one construal of such spacetimes, they're worse than merely non-globally hyperbolic. That's the punchline, right?
But why should we, I mean, why should we think that we can assign a classical causal structure to an evaporating black hole spacetime? Wouldn't we naturally think that we'd have to talk about quantum?
I couldn't agree more. I couldn't agree more. I think that the eventually we'll be able to understand these spacetimes well enough, and we'll be able to look back at this and say, oh, you know, this is what we used to think, or this was one way of doing it back in the day. But what I'm merely trying to do is to say, can I use the resources of Lorentzian geometry? Can I use the resources of these, you know, is it okay to, or not is it okay, can I use the resources of classical Lorentzian geometry to characterize what I mean in the rough by an evaporating black hole spacetime? And if so, what can I deduce from that characterization? The nice thing is that you get theorems, you get rigorous, precise theorems, but I agree with you.
But they might not correspond to the actual situation.
Sure.
Well, if you just remove a time, so we have, I think, good reason to believe that space-time is going to be essentially classical almost everywhere, except in a tiny little neighborhood around the evaporation point. If you just remove that tiny little neighborhood,
The quantum fluctuations in the evaporation point go like the square of the black hole mass divided by the Planck mass. So it's not really a point, right?
No, I mean, but I'm saying when the black hole gets small enough, if we believe the evaporation picture, you know, far enough down, so that we think that quantum effects will take over, but there's still some kind of evaporation happening. We just isolate. We just take that little space-time, the analog of that space-time region in the classical picture. Just remove it. It's just going to be basically removing a little circle right around there.
But it's not a little point because
results the whole.
the spread in the wave function is of order m squared.
So you're claiming that the quantum effects will destroy our capacity to talk about classical causal structure, you know, all the way up to
No, I'm saying that, well, it's certainly true that, I mean, it's a simple calculation that it's not a localized point, right? Because the spread of momentum.
Yeah, it's not a point.
I'm not claiming that. I'm saying there's no argument that quantum effects are unimportant.
Okay.
Yeah, no, I mean, I'm totally sensitive to this, and I'm not saying that this is the right physical description. I'm merely saying that if you wanted to exploit the resources of this mathematical framework, then here's a way of doing it. So I don't know if this is, I mean, I'm sure it's not the right physical description. I'm sure there's a quantum theory behind this that'll do the work for us, but I'm saying that, you know, if you believe that a light ray in some region far away from the evaporating black hole still defines some notion of causality, then these arguments have a certain appeal to them. But again, I agree that I'm sure there's a quantum theory underlying this that will make this whole kind of approach kind of old-fashioned, or, you know. But it's, well, if I restrict myself to a precise, well-defined, rigorous mathematical theory of causal structure in space-time, what can I do? Well, I'm claiming this is what you could do. But again, I'm happy to. So, okay, so I think I've kind of delivered the punchline. But now I wanted to talk about some physical implications. Well, I think the physical implications, we've talked a little bit about them. As for the philosophical implications, I think they're kind of interesting. So I'd like to talk about them to some extent. So I'm just going to move this door a little bit to give myself a little bit more space. So I think the philosophical implications are kind of, I think it depends on your temperament as to how seriously you take this. I'm sure there's some people in the room who are, hard-nosed physicists and who think that philosophy is a kind of like something from the past or something. I myself find this kind of fun to play around with the philosophical implications, though I'm not really versed in that either. I have to talk to Eric to get me and to explain, or to Faraz to explain these things to me. But anyway, one thing which I want to talk about is unique global evolution. And this is essentially a mathematical problem, but it's very interesting when you adopt this structure. You can kind of consider this problem in a very nice and rich way. The other is more distinctly Greek, or Copernican. I'm about to write Greek. What am I doing? Copernican principle, kind of old school, but I kind of like this one. Eric showed me why this would be relevant. 3 is going to be some kind of metaphysical bias, and this is, I think, probably the most interesting one. And actually, we'll come back to quantum arguments later on. I think this will be interesting. So, the problem about unique global evolution. So here's, in short, what happens. If I have Minkowski spacetime and I remove a point, and I consider some data here, and I evolve this data, then this spacetime is not globally hyperbolic, so you'd think that actually I don't have unique global evolution. But in fact, that's incorrect. If the PDE has a certain, if the relevant PDEs has certain properties, for example, in the Masters-Klein-Gordon, I can show that actually I can evolve the data up to this light cone. By continuity, I'll have data on the light cone, and then I can do a Cauchy problem from the light cone and get the results of the evolution here. So in fact, you can have a non-globally hyperbolic spacetime and still have unique global evolution. So what about a causally discontinuous spacetime? Well, in fact, nobody knows. There exists no general theorem of the kind, if the spacetime is causally discontinuous, then unique global evolution fails. So an interesting kind of conjecture is what's the tension between causal discontinuity and 1? Nobody knows, and I think from the mathematical point of view, that's very interesting. From the physical point of view, it's also interesting. I mean, do these spacetimes, at least within some classical idealization of them, do they permit global evolution? The second point, the Copernican principle, is as I said, slightly more philosophical. The point here is to say that essentially the notion of causal discontinuity is a definition which is supposed to capture, in a sense, the following idea. Consider a point P in space-time, consider some neighborhood of that point, U of P, consider the past light cone of this point, P. Now consider what happens if I consider some Q in this U of P. What causal continuity basically requires of a space-time is that for sufficiently small neighborhoods of points, nearby points, so between, for example, Andy and me, for example, we're nearby more or less, then our past cones are going to be roughly similar. They're going to change in a continuous manner. That's what causal continuity is more or less supposed to capture. If I have a failure of that, then it's a kind of important metaphysical principle which we usually have, which is going to be the point 3. But basically, the idea that all points are observationally more or less equivalent, or that the epistemic predicament of you and I and us and everybody else in the room is more or less changing in a continuous manner across space-time variations. Well, that's obviously going to be subject to revision if we buy this argument. If we buy that space-time is causally discontinuous, then in fact, this idea that nearby points have the same past is just not really okay. And you can think of this as well by considering some future point here and considering a past light cone here and considering some neighborhood here. If I'm south of this neighborhood, then my past light cone is just some relatively flat, decaying, or asymptotically flat portion of space-time, which isn't that bad, seemingly predictable, but suddenly, coming up to P2, I'm starting to receive things from a naked singularity, whose existence has been proven in the theorem. So this is a kind of issue if we buy the Copernican principle. And finally, metaphysical bias. Well, another way you could cash out the definition of causal discontinuity, say by considering Minkowski space-time with a line removed. So this is Mink minus some line, some integral with the usual Minkowski metric. Then if I consider a point here, then its past light cone is in fact like this, but I consider another point here and its past light cone is in fact like this. Now suddenly consider what happens to a neighborhood at this point. Well, you'll notice that if I'm just slightly next to it, right, then suddenly my past light cone includes all of the rest of space-time, all here that my nearby point couldn't see. So notice that the scope, the covering of the space-time by your own past may change discontinuously, simply by moving 1 meter to the right. This is a rather strange consequence. Similarly, this definition of causal continuity, which by the way originated in the work of Hawking and Sachs from '74, similarly, you can get the idea that in fact for metrics which are near, so this is some g, this is some reference g, I consider some g which is g0, which basically whose light cones are slightly more opened, then what that's saying is that the world is slightly different, right? From the metaphysical perspective, we think that if the world was slightly different, things wouldn't be that different. But actually, again, that fails, considering a causally discontinuous spacetimes whose past light cone is like this, and then if I consider a slightly wider one, some perturbation of the metric, suddenly my past light cone again changes in a discontinuous manner. So the two metaphysical biases that we have, namely that if you're here, or rather than here, then our paths are roughly the same, or if you're here and the world was slightly different, then your paths would still be likely the same, in fact those fail. Those fail dramatically for causally discontinuous spacetimes. So that's a kind of interesting outline. Another thing which is nice, and this is a more physical consequence of the theorem, is that by the theorem you can also prove that spacetimes which are of this kind have to be non-stationary. That's rather nice because when we do all kinds of QFT and curved spacetime modeling, well, we always kind of assume these asymptotic killing fields. Suddenly, if you have a spacetime which is of this kind, you can show that actually the spacetime doesn't admit such a killing field, such a time-like killing field. That's a cute consequence as well. Anyway, after all that, I think I've took enough of your time, so thanks for everything.
Coming back to Andy's point, how do you expect these conclusions to change if you introduce a theory that has quantum mechanics and gravity?
So, I mean, I would really have to defer to the experts in quantum gravity, but my basic, very, very rudimentary understanding of what's going on here is that Hawking radiation doesn't play a role for a long time until it gets to the near enough to the relevant scales. And then I'm guessing that basically if I'm considering things very classically, I'm looking at the evaporating black hole from a long distance away, I can basically, and this is a total guess, and I would love some experts to tell me if this is at all relevant, like at all misguided or whatever. I would take a rough kind of guess that the weird stuff is going on in some region. And I would take a rough guess that actually if I'm here, my past light cone some way away from this guy, of course the notion of distance will have to be made precise, which is not going to be easy. But basically, my rough guess is that the weird stuff is going there, the quantum effects are going to be going on here, and if I'm far away from the black hole, then actually I'm more or less in a semi-classical picture. That's my rough guess. Now, if you buy that, which again, I'm not saying I have a rigorous argument, but if you buy that, then all of this applies. Because S1, S2 can be partial Cauchy hypersurfaces. That just means the space-like slice through spacetime, and that can be taken arbitrarily far in the future, in the past, of whatever weird stuff is going on. So, namely, my guess is that if quantum gravity tells us that everything is screwed up, then this tells you nothing. If quantum gravity tells us that things are screwed up only within some vicinity, to be made precise, because the notion of vicinity is going to change depending on the theory that we're using, but if the weird stuff is going on within some vicinity of the black hole, then all of this applies. So that's how I see it.
Yeah, so you made some assumptions that led you to derive a theorem for evaporating black hole spacetimes, and that gave you these weird implications. Now, don't you have to show that these implications, which now could happen anywhere in spacetime, I guess, do actually not happen anywhere in spacetime, and why they're only relevant for when you have black holes?
So, I mean, that's a great question. One of the nice things about this theorem is that it actually permits you to localize things. So, in fact, you'll show that the failure of past reflectivity happens on the Cauchy horizon from S1. So, in fact, what you're saying is made precise by the theorem, because the theorem tells you actually the weird stuff is only going to happen within some portion of the spacetime. So it doesn't, as you say, happen everywhere. I mean, I would like someone in quantum gravity to tell me if my very, very vague, rough, like back of the envelope idea that whatever quantum gravity does, it does so within some contained region somewhere around the black hole. If that's a valid intuition, which I have no idea if it is, but if that's a valid intuition, then there is some more support for this kind of work. If in fact that's not at all what happens, and that things are totally different, then of course none of this would apply. So in particular, if there's a firewall, then I don't think it's...
So the information paradox may be linked to that in some sense, right?
Yeah, so I mean, I think if you pin yourself into that, then you're pinned into the information paradox.
Right.
So, and one of the things that my collaborators and I have been arguing is, in fact, that very long wavelength modes, so-called soft modes, which are produced in infinite numbers. There's infinite many. I mean, even in E plus E minus scattering, there are infinitely many soft photons. So there are infinite number of soft modes that are created, and they have to be kept track of. And that's certainly, in doing this, you are assuming they are not relevant.
Do you have any sense from your calculations whether the quantum fluctuations will be big enough to disrupt an attribution of something like classical causal structure far away?
I'm not sure I know what that question means. It's certainly, you mean at null infinity?
Yeah. Or in a neighborhood.
And how do you characterize this? I mean, how do you characterize the causal structure at null infinity?
I mean, I guess one way to make it precise is to ask, is the semi-classical approximation valid? Because that assumes classical causal structure.
Yeah, I don't know the answer to that question. But I guess I would also say I don't think it's been shown the answer is yes.
Definitely.
Well, you can turn it around and say, if you don't want these pathologies, something has to happen of the type that Andy is talking about.
In fact, there are an infinite number of conservation laws that connect what's inside your circle to what's at infinity. And you could say they're not important, and maybe they're not, but it hasn't been, I don't think it's been shown.
So these, what's the notion of scattering being used? Like, you're saying there's a past and there's a future,
Yeah.
And how are we relating the two? What is the? It's not going to be some classical evolution, right? It's not a PDE problem, not a Cauchy problem. So there's conservation. I mean, I need
Well, it's
to.
a quantum state. Well, I mean,
Okay.
one would start. I mean, I think one would start with the hypothesis that there's a globally defined quantum state, and it would be natural to start with that and not give up on it until beaten to death. Because the alternatives seem pretty grim.
You really like that assumption, Andy.
I'm not alone.
Well, Feynman said everything is quantum.
I believe that, but I'm not sure. I might give up the assumption just before death.
Okay, well, Martin's around until early May, I think, so if you want to chat to him, there's plenty of time to do that. Perhaps we can thank him.
It was very nice.
That was really beautiful. Really nice job.
Почему?
Uh,